Neurons communicate with each other using the language of electrochemistry. And to appreciate how information is transmitted across large distances, in some cases over a meter, it's necessary to understand how action potentials work. But first, let's review the basics of neuronal communication. Neurons have two important jobs. One is to transmit a message to a target across a synapse, and the other is to carry a message along the length of the axon to the next neuron. The first job is made possible by neurotransmitters released from the presynaptic neuron. They trigger graded potentials in the postsynaptic neuron, which come in two flavors: excitatory postsynaptic potentials, or EPSPs, and inhibitory postsynaptic potentials, or IPSPs. The neuron has the ongoing task of adding up all the EPSPs and IPSPs to determine when to start the neuron's second job of carrying the message down the length of its axon. If the membrane potential reaches its threshold of minus 55 millivolts, a type of electrical signal called an action potential is generated. The action potential then triggers neurotransmitter release once it reaches the terminals. And the process starts all over again in the new neuron. Although an action potential is first generated where the membrane potential reaches minus 55 millivolts, which is usually in the axon initial segment right at the soma, we'll focus on the events in the axon, since their main job is to propagate the action potentials to the neuron's target at the terminals. The first step of an action potential is opening of voltage-gated sodium channels. As a postsynaptic neuron receives neurotransmitter signals, if the threshold of minus 55 millivolts is reached, a special type of sodium channel that's sensitive to electrical changes gets opened. Let's take a quick look at how different receptor types distribute in a neuron. Unlike the receptor channels in the synapse that are neurotransmitter gated, that is, they open in response to specific neurotransmitter binding, voltage-dependent sodium channels, which are most densely located in the axon, open when the membrane potential is depolarized to minus 55 millivolts. In a resting neuron, there are more sodium ions outside the neuron than inside, so there's a chemical and electrical imbalance that promotes sodium movement inside the cell. Thus, when voltage-dependent sodium channels open, sodium rushes into the neuron, bringing its positive charge, making the cell even more depolarized. Once an action potential is initiated, it propagates along the axon to its terminals. If we think about the nervous system as a whole, hundreds of millions of action potentials are being fired on top of one another at all times. Thus, the nervous system must operate within a remarkably sensitive computational time frame. Indeed, some action potentials can travel at speeds of up to 100 meters per second. One strategy the nervous system uses to increase action potential speed to as quick as possible is the surrounding of axon shafts with the fatty membranes of glia cells. In the central nervous system, oligodendrocytes form fatty myelin sheaths along axons, as seen here. This insulates the axon, allowing electrical charge to quickly jump between myelin within the axon. The space between the myelin sheaths are referred to as nodes of Ranvier. If we zoom in into a node of Ranvier, we see that this area is densely clustered with ion channels, which allow the passage of electrical charge in the form of ions across the membrane in areas not covered by the myelin. Let's now take a closer look at the mechanisms behind an action potential's travel down the axon away from the soma to the axon terminals. Here, we can see a neuron with its axon extending away from its soma. If we take a cross-section along the length of its axon and zoom in, we can start to appreciate what's happening inside the neuron's axon. When the graded potentials at the synapse add up to minus 55 millivolts, this is detected by the voltage-dependent sodium channels, which are found in large numbers along the axon. As the voltage-gated sodium channels open, sodium rushes into the axon along its electrochemical gradient, bringing its positive charge into the neuron. This depolarization is then sensed by neighboring sodium channels, which also open when the membrane potential reaches -55 millivolts, having sodium ions in positive charge rush into the neighboring region of the axon. At this time point, if we were to stick an electrode into the neuron, we would see the membrane potential rise at the location where the sodium channels are opening. At this time point, this location is proximal to the soma. That is, it is closer to the soma than the terminals. The wave of depolarization makes its way down the axon as neighboring sodium channels along each part of the axon open, allowing sodium to continue to flow in. This depolarization wave travels in a proximal to distal direction. At a time point 2, if we were to again stick an electrode into the neuron, the depolarization would be measured farther down the axon. This process of sodium channels bringing positive charge, which then opens adjacent voltage-dependent sodium channels, works its way uninterrupted all the way down the length of the axon. So, once an action potential gets started, it doesn't stop until it runs out of neuron. While voltage-gated sodium influx is a key mechanism of action potential propagation, it is only half the story. Let's return to where we started, at the beginning of the axon. In review, when the neuron is depolarized to -55 millivolts from graded potentials, voltage-gated sodium channels open. This allows sodium to travel across its electrochemical gradient from outside the neuron to inside the neuron. This causes a further depolarization of the neuron to +40 millivolts. When the membrane potential reaches +40 millivolts, two things happen. One, voltage-dependent sodium channels inactivate, and two, voltage-dependent potassium channels open. Keep in mind that potassium is more concentrated inside the neuron, so when its channel opens, its concentration difference is a driving force for potassium movement outside the neuron. At a membrane potential of +40 millivolts, there is also an electrical reason for potassium to leave the neuron. When positively charged potassium leaves the neuron, it brings its positive charge outside the neuron with it, which makes the membrane potential inside more negative and helps to balance the charge difference of the sodium influx. Let's come back to the electrical voltage recording of the axon at time point 1. If we zoom in, we can notice there are two main components of the action potential. First, when the cell reaches -55 millivolts, it triggers an exponential rise in the membrane potential to +40 millivolts. This rise is a product of sodium influx through voltage-gated sodium channels. Once the action potential reaches +40 millivolts, its second component can be seen. The membrane potential falls back to its negative resting membrane potential. This is due to the closing of voltage-gated sodium channels, and more importantly, the opening of voltage-gated potassium channels, which allow the potassium efflux out of the neuron. This is the repolarizing phase of the action potential. So, if we come back to watch our action potential travel down the axon, at each step along the axon, voltage-gated sodium channels open, followed by voltage-gated potassium channels. Understanding the voltage changes across the membrane as the action potential moves down the axon is essential to understanding its propagation mechanisms. So, let's again review the changes across the membrane during an action potential, except one step closer. At rest, when the neuron is not receiving any input, its membrane potential is at about -70 millivolts. All the voltage-gated sodium and voltage-gated potassium channels are closed, such that very few sodium ions and very few potassium ions are moving across the membrane. If the neuron gets enough excitatory postsynaptic potentials, and not too many inhibitory postsynaptic potentials, it will reach the threshold of minus 55 millivolts, and the voltage-dependent sodium channels will open, allowing for sodium influx. This is called the depolarization phase, which is the part of the action potential where the membrane potential climbs all the way to positive 40 millivolts. At positive 40 millivolts, the sodium channels deactivate, and the voltage-dependent potassium channels open. Potassium leaves the neuron along its electrochemical gradient, taking its positive charge with it. This is called the repolarization phase, since the membrane potential returns back to minus 70 millivolts. For a brief period of time, potassium keeps moving out of the cell, hyperpolarizing the neuron so it sits at less than minus 70 millivolts, which ensures that this segment of the axon will be unlikely to fire off another action potential. This is called the refractory period and ensures that the action potential only travels in one direction. Finally, once the action potential is finished at a certain region of the axon, the neuron uses special pumps to restore the ions to their original concentrations, and only then is that segment of the axon ready to fire again. Let's put this all together by considering a snapshot that captures all the voltage changes over the duration of an action potential from beginning to end. Keep in mind that this is happening all over the neuron, but we're just looking at one small segment of the axon. First, let's focus in on graded potentials, which lead to action potential initiation. However, unlike action potentials, which are all or none, graded potentials vary in size. As shown here, graded potentials can lead to different sizes of depolarizations or hyperpolarizations. In contrast, action potentials happen the same way every time they're triggered. So, the strength of an action potential is coded by frequency, or the number of action potentials per time period. A strong signal will produce more action potentials than a weaker one over the same period of time. Our knowledge of how ions work to generate action potentials has allowed us to manipulate the process to our advantage. Let's focus on the depolarizing phase, which is strongly dependent on voltage-dependent sodium channels. When the sodium channels open, sodium rushes into the cell, kicking off the whole process. So, what happens if these channels are blocked? Say you need to have dental work done that requires drilling. Not a pleasant experience for most people. Most dentists give an injection of a drug, like Novocaine, that deadens sensations in the mouth. Indeed, most local anesthetics used in dentistry are sodium channel blockers, which means they prevent the depolarizing phase so an action potential can't happen. An interesting fact is that drugs like Novocaine were originally derived from cocaine, which is one of the only few naturally occurring local anesthetics. Part of the cocaine molecule acts as a sodium channel blocker, so it produces a numbing feeling if rubbed on the gums. By modifying the cocaine molecule, scientists were able to keep the sodium channel blocker activity, but remove the parts of the molecule that promoted addictive behavior. How about this cartoon fish? What does it have to do with action potentials? This is the pufferfish, which contains a poison called tetrodotoxin, concentrated in certain organs like the ovaries and the liver. Pufferfish can kill you lots of ways. If threatened by a predator, they may puff up, which is how it got its name. You can actually die from eating certain body parts of the pufferfish that contain tetrodotoxin. Tetrodotoxin is a powerful sodium channel blocker, and even tiny amounts can lead to paralysis and death by blocking action potentials in the respiratory system. So far, we have discussed how an action potential is initiated, and then how it propagates down the axon. However, what we haven't discussed yet is what happens when an action potential reaches the axon terminal. Once an action potential arrives at the terminal, the depolarizing wave opens up another type of channel, the voltage-dependent calcium channel. Like sodium, calcium is more concentrated outside the neuron, driving its movement inside the neuron. Calcium is necessary for neurotransmitter release through a process called exocytosis, where the presynaptic vesicle fuses with the terminal membrane to release its contents into the synapse. Now, it's important that neurons are responding in a time-dependent manner so that their activity is connected to the tasks we're trying to accomplish. For example, if I were to tell you right now to think of your first ever teacher, you probably didn't activate that memory until I asked you to. At some point before the end of this video, you'll probably stop thinking about your first teacher. So your memory neurons turn on and off when they are needed. Just as it is important to initiate a neuron's response, it's as important for neurons to terminate that response when the job is done. There are two main methods to terminate a neuronal response, and they both involve removing excess neurotransmitters from the synaptic cleft. The first way neurons terminate neurotransmission is by presynaptic reuptake, which uses specialized transporter proteins that span the presynaptic terminal membrane. These transporters relocate the neurotransmitter molecules so that they can be repackaged into synaptic vesicles and used again at a later time. Drugs like SSRIs, used to treat depression, work by blocking the reuptake transporters for the neurotransmitter serotonin, allowing it to hang around in the synapse for a little longer. Low serotonin has been implicated in depression symptoms, so by elevating its levels in the synapse, these drugs attempt to treat the disorder. The second way neurons terminate neurotransmission is by enzymatic degradation. Enzymatic degradation is the metabolic breakdown of neurotransmitters in the synapse. You can think of it as the neurotransmitters essentially being eaten up so they no longer have biological activity. A great drug example that takes advantage of enzymatic degradation in the synapse is the Alzheimer's drug donepezil. This drug blocks the breakdown of the neurotransmitter acetylcholine, which is reduced in the brains of Alzheimer's patients. This allows it to hang around in the synapse longer and boost memory signals that decline with the disease. Taken together, the action potential is perhaps the most quintessential process of the nervous system. It is responsible for transporting signals around the nervous system in remarkably fast times. Amazingly, humans, as well as other animals, like the pufferfish, have figured out ways to alter aspects of the action potential, hijacking the signaling of our nervous system.